Hey everyone, welcome to Practically We Bring Learning Alive. As you all know, the CBSE Term 2 exam has been scheduled on 26 April and you all must be preparing for it, right? So to help you in your preparation, we have brought one short videos on our Practically 11th and 12th channel, okay? Where we're gonna cover all the subject physics, chemistry, biology, and we'll be having all the chapters covered in those one-shot videos. So my name is Mayur. I'm your chemistry teacher. I'm going to cover all the chemistry chapters which you are preparing for your term 2 exam. Okay, we're going to start with a one-shot D block and F block element. Okay, so where we'll be covering all the things, what are the different properties of D block and a block element, their electronic configuration, their physical properties, their usage and whatnot. Okay, chalo, let's begin. So this is the periodic table, as you all know. Okay, complete periodic table. Herein you have a S block element, P block element, A block element, and here you have what? You have a D block element, right? So these are your D block element. So this is your 3D transition series. This is your 4D transition series. Here you have a 5D transition series, and lastly you have a 6D transition series. Now 6D transition series is obviously incomplete. If you're talking about the first transition series, which is also called as 3D element. 3D element stands from atomic number 21 to 30, scandium to zinc. Then you have a 4D element. 4D element starts from atomic number 39, finish it around 48, cadmium. Then you have a 5D element. So whenever you have a 5D element, remember it starts from lutetium. After that, it starts from lanthanum. You have a lanthanum here. Okay, at 57 you have a lanthanum. Now between lanthanum and this lutetium there are 14 elements, and those 14 elements are what? These are those 14 elements. See, lanthanum is here, 57. So this 57 to 70 you have this element, and from 71 starts your D block element again. So lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, Au, Hg, like that. Similarly for actinide element also, it starts from actinium 89, and from 89 to nobelium 102 you have a block element. After that, from 103 again starts your 6D transition series, and that is how D block, F block elements are, or I would say, not actually spreaded, but that is how they are presented. Okay, D block elements are called as transition elements, and F block elements are called as inner transition element. Now, why do we call D block element as transition elements? Let me tell you. See, these are your S block element, and what are this? These are your P block element. Now, between your S block and P block, there is a D block element. See, S block elements are typical metals. They are typical metals. They are actually known as metals are being represented for S block element only. Typical metals. P block elements are what? They are typical non-metals. So as you go from S block to P block, they are changing. They are changing from metallic to non-metallic. They are changing from metallic to non-metallic through or via D block element. So that means through D block element, transition is happening, or I would say change is happening. Through D block element only change is happening, and that is why they are called as transition element. That is, through them change is happening. Okay, and F block elements are called as inner transition because they are present in the transition element, which are D block. That is why they are called as inner transition element. That is how the whole naming of there is all about. Okay, chalo, moving ahead. Now, electronic configuration of D block element. Now you need to understand one point here. See, if you start from scandium, how do you write the electronic configuration? It is quite easy. 4s2 3d1, 4s2 3d2, 4s2 3d3, like that. We know that. Till here it's argon, right? 18. Then 19, 20, 21, like that. Here you have what? Here you have a krypton, here you have xenon, and here you have a radon, right? That is your what? Those are your noble gas elements electronic configuration. Okay, now after them you start with these metals. Okay, but you will see there are some exceptions here. For example, look at here, chromium, then at copper, you will see exception. Now why exception was present at chromium? Because half filled d orbital was there, 3d5, right? So see, scandium is 4s2 3d1, titanium is 4s2 3d2, vanadium is 4s2 3d3. Your chromium could have been 4s2 3d4, but what does it do? It takes the one electron from s to fulfill the d orbital. So that d orbital now has 5 electrons, half filled d orbital, right? Because that gives it extra stability. So that is why it became d5. Same thing happens here also. Same thing happens here. Nickel is 4s2 3d8, right? Copper can easily could have been 4s2 3d9, but it became 4s1 3d10. Why? It takes one electron from s orbital to make the complete fulfilled d orbital, because that gives it extra stability. Okay, now till 3d series is quite fine. Okay, but there are some notable exceptions in 4d series. I'll show you how. See, look at here, yttrium, zirconium, niobium. Now zirconium is 4s2 your niobium could have been 4s2 Now there is no question here of half filled, but still it took one electron from the s to become 4s2 5s1 Any reason? We don't know. There is no reason as such for it. Same thing happened here, ruthenium, and lastly at palladium also. So if you want me to tell you the trick is quite simple. Okay, how do you remember it? For this 3d series, the exception is at 1, 2, 3, 4, 5, 6, 7, 8. Fourth element and eighth element. Fourth element and eighth element, there is an exception. Similarly, for 4d series, third, look at this, third metal, 4, 5, 6, 7, 8, 368. Basically, you need to remember 368 for 4d series. For 5d series also there are some exceptions. Look at here. You go here, here. Look at this, platinum. This is 8 number. So these are some of the metals where you will have an exceptional electronic configuration. At some places I can tell you the reason, because there is a half filled orbital, full filled orbital. There is some logic in some exceptions, but not everywhere, and that's the issue. I know. See, chromium, same thing happens here also. So I did not consider these as an exception. Same thing happens here. Look, chromium achieves its half filled electronic configuration. Similarly, molybdenum also achieves its half filled electronic configuration. But when it comes to tungsten, which is just below them, at tungsten it doesn't happen. So you will really wonder, then why doesn't it happen at tungsten? If the half filled orbital was really a criteria of stability, it should have happened at tungsten too, but it did not happen in tungsten. So that's where, and that's how the chemistry is. That doesn't make the subject less interesting though. Okay, it's just that we set some hypothesis for a given concept, for a given subject, and we think the species or the element or metals or whatever it is should behave like the way we have predicted, but nature has always something in its mind. Okay, anyways, so this is what the whole exceptional electronic configuration of D block element is all about. Okay, sure. Moving ahead now, physical properties. The lattice structure of transition metals. See, transition metals are, they adopt the crystal structure also. Obviously they adopt the crystal structure, and those crystal structure there the different metal adopts a different lattice structure. How? Let's see the complete. See, scandium, titanium, they achieve HCP, hexagonal close pack structure. Vanadium, chromium, manganese, iron, they achieve the BCC, body center cubic structure. Again, cobalt achieves HCP, nickel, copper achieves FCC, like that. Okay. Now there is no certain pattern to it. Like this metal would adopt that crystal structure, that metal would adopt this crystal structure. There is no certain criteria to it, and questions generally do not been asked on those things also. Okay, it's just that you should know it. That is why I am telling you. Okay, the next things, trends in melting point of transition elements. Now here this point is really catchy, and this is really interesting. Now we know that when you start from scandium, titanium, vanadium, chromium, see, whenever you're talking about chromium, how do you write the electronic configuration of chromium? Chromium's atomic number is 24, right? So its electronic configuration become argon 4s1 3d5. So if you're talking about unpaired electron, how many unpaired electron does your chromium has? Unpaired electrons. Your chromium has 6 unpaired electrons. Now you need to understand one thing here. You can see here, let me change the color once again. Okay, I'll take this color. Okay, this chromium, see, atomic number is increasing from scandium to copper or zinc. Okay, chromium is right at the top. Okay, then you have a magnesium at the top. Sorry, my bad. Molybdenum at the top, and then you have a tungsten at the top. What do you observe from this? What was the electronic configuration of your molybdenum? Let me show you. Just look at this. Molybdenum. It also, look at this. This has a 6 unpaired electron. Chromium has 6 unpaired electron. Molybdenum also has a 6 unpaired electron. Then you have a tungsten. Tungsten has not exactly 5, but yeah, it has 3 unpaired electron like that. So now when we go to our original, just a sec. Oh, what am I doing? Yes, there we are. Look at this. Chromium has 5 unpaired electron. Chromium has 6 unpaired electron. Molybdenum also has 6 unpaired electrons, and tungsten has somewhere around 3 or 4 unpaired electrons. So do you find any relationship with this? Yes, there is a relationship between number of unpaired electrons and the melting point of transition metal. See, the melting point of your transition element is directly proportional to number of unpaired electrons. It is directly proportional to number of unpaired electrons. More the number of unpaired electrons, more is the melting point. It is that simple. Because when more and more free electrons are available, the bonding becomes more and more strong between the atoms. As the bonding becomes more and more strong, the melting point becomes higher and higher. Okay. Now, see, as far as this number of unpaired electrons and melting point is concerned, it is quite clear to you. But yes, there are some cases where not exactly an exception, but yeah, irregularity is there. For example, look at here. After chromium, manganese also has 5 unpaired electrons, but its melting point is quite lower even than vanadium, titanium also, and chromium also. Why is it so? In fact, chromium's melting point was higher because it was having more number of unpaired electrons, okay, than scandium, titanium, vanadium, and manganese also. Fair enough. But manganese has unpaired electron more than vanadium. Vanadium has how many? 3 unpaired electrons, okay, but manganese has 5 unpaired electrons. So if really it was the number of unpaired electron thing, manganese melting point should have been higher than vanadium, and that is why I need to tell you second point. It is not always necessary that number of unpaired electrons correlate with the melting point. Sometimes it is the weak crystal lattice of your metal also. Sometimes metal lattice is weak. So you can't help, even if you have more number of unpaired electrons, your crystal lattice could be weaker. And when your crystal lattice is weaker, the melting point is going to get weaker. That is the reason for manganese, technetium and rhenium to have lower melting point than their preceding metals. Okay, I hope this picture is pretty much clear to you. But if it has been asked in that way, if there is no such thing, I mean, if there is no chart available to you, then you should understand the number of unpaired electrons and melting points, they are correlated, so that it would be easy for you to find out trends in the exam. Okay, sure. Moving ahead, the next is trends in enthalpies of atomization of transition elements. Again, enthalpies of atomization, as I again told you, enthalpies of atomization is connected with what? Lattice energy of your metal. Lattice energy of transition metals is extremely high. It is very, very high. And as the atomic number increases, enthalpies of atomization also increases. You can see here, this is the 5D series. See, you can see here, this is the 5D series, 4D, 3D. 3D series is at the bottom, 5D series is at the top. What do we mean by that? As the atomic number increases, I mean, if you are comparing between 3D, 4D and 5D series, then higher the atomic number, higher is the size. I would rather say they are in the next group. This is not about actually atomic number, it is about present in the next shell. So when 4D series is present in the next shell to the 3D series. So obviously size wise 4D is larger in size. Similarly 5D is also large in size. So those factor contributes for them to have higher enthalpy of atomization. Okay, sure. Moving ahead. Now variation in atomic and ionic sizes of transition metals. Now we all know, see, there are two factors. Okay, before going to the two factors, let's discuss it linearly. In periodic table, whenever we are discussing about size, how does the size varies? When you go from top to bottom in the periodic table, what happens? The atomic and ionic size increases. Why does it increases? Because whenever you go from top to bottom, each incoming element, the next shell has got added. So whenever the next shell is getting added, it is obvious that size is going to get increased. Okay, but the picture is not that straightforward whenever we are talking about element going from left to right. Because when you go from left to right, what is happening? Atomic number is increasing. When atomic number is increasing, what happened? Atomic number means what? Number of protons are increasing. So when number of protons are increasing, the nuclear charge, right? The nuclear charge is also increasing. And what does increased nuclear charge do? Nuclear charge basically means what? The attraction of nucleus to the electrons. So nuclear charge, increased nuclear charge does what? Increased nuclear charge pulls the shell inwards. So when it pulls the shell inwards, what happened? Size will keep on decreasing. Because when you go from left to right, electrons are getting added to the same shell. Electrons are getting added to the same shell. So there is no question of size increasing. Suppose there was no nuclear charge, then size should have been constant, because you are adding electrons to the same shell. Okay, but nuclear charge is there. With each added electron, the nuclear charge is keep on increasing, and that extra added nuclear charge pulls the shell inwards towards nucleus, and that is why when you go from left to right in the periodic table, size always decreases. Okay, but that is applicable to overall periodic table elements. Okay, if you are talking typically or particularly about transition element, the picture is different. And how it is different? Let's see. See, the factor which I just told you, that size decreases, is applicable from scandium, titanium. See, scandium, titanium size has decreased, vanadium size has decreased, chromium size has decreased, manganese size has decreased. In fact, till iron also size has decreased. Okay, or let's consider it till chromium only. Okay, till chromium size has decreased considerably. Okay, now as you go from chromium to zinc via manganese, iron, cobalt, nickel, copper, what do you observe? That size is practically constant. The size here, as you go from chromium to copper, is practically constant. It doesn't change significantly. Why? Well, that's where the catch is. I just told you, when you go from left to right, the nuclear charge increases. When the nuclear charge increases, it pulls the shell inwards, because of which the size decreases. But there is another factor here. See, till chromium you have added what? How many electrons in d orbital? 5, right? After chromium, when you go through manganese to iron, cobalt, nickel, copper, and then zinc, the number of d electrons are getting added more and more. See, till chromium you have 5 electrons. Okay, those 5 electrons are completely unpaired. In manganese also you have 5 unpaired electrons. Okay, but from iron, the pairing in a d orbital starts happening. Iron has d6, cobalt has d7, nickel has d8, copper has d10 again, and zinc also has d10. Okay, so I'm not saying this pairing causes this thing. What I'm saying is that the electron starts pairing in d orbital. In other words, there's a more accumulation of d electrons. And what does d electron do? See, with each added d electron, the nuclear charge has increased, but shielding hasn't happened that much. See, d electrons, they are the weak, they show or they display the weak screening effect. And because of that weak screening effect, see, what does nuclear charge do? Increased nuclear charge decreases the size. Okay, and with each added d electron, those d electron nuclear charge is increasing, but the shielding effect does what? Shielding effect does not let nuclear charge to reach till the last shell. So because they show the weak shielding effect, because of that, what happened? Both these opposing factors try to balance each other. The shielding effect of d electrons and increased nuclear effect, both these factors try to oppose each other, and that is why when you go from chromium to zinc via copper, size does not change that much. Practically, it stays same. Okay, but when you go from copper to zinc, you can see the size has increased. You can see here the size has increased here. Why? Because in zinc all the electrons are paired now. The electronic configuration of your zinc is argon 4s2 3d10. So you have all the electrons in s and electrons in d orbital, all of them are paired. Where all the electrons are paired, there is inter-electronic repulsion. And inter-electronic repulsion would do what? It would make the system unstable. And as I told you earlier also, that no system wants to be unstable, right? So what does it do? It tries to expand its shell a bit. Its shell increases a little bit. Because of that increased size of your shell, repulsion decreases. And that is why whenever you can see all the element, you can see here copper, when you go from copper to zinc, whenever you go from silver to cadmium, whenever you go from Au to HgC here, size has increased. Why? It's because of inter-electronic repulsion only. Okay, that is for 3D series. Now, when you go from 3D to 4D series, see the difference. 4D series is considerably larger. 4D series element size is obviously greater than 3D series, which is obvious, which is expected, right? This is 3D series, this is 4D series. In 3D series, 3D orbital is coming. In 4D series, 4D orbital is coming. So the next shell has come. No. So size is obviously increasing. That is why the marked difference of size between 4D and 3D element is there. Okay. But do you see the same difference as we have for 4D and 3D between 4D and 5D element? No, we don't have. See, this is 4D, This is 3D. Difference is marked. But between 5D and 4D, see, difference is very, very small. Why? Why it is like that? See, the 5D should have been here now. But it is not like that. 5D transition metals, though they are coming into the next, shell number of 4D element. The next shell has come, obviously. So the size should have been more, but in between 4D and 5D element, there are what? There are F block element. Yes, the inner transition elements are there, and they are the weakest shielding counterpart. They show the weakest shielding effect. Their shielding effect is weakest, because of which the increased nuclear charge gets dominated. Because the 14 F electrons has got added, no. So those 14 F electrons has increased the nuclear charge to significant level. But those electrons do not shield the nuclear charge. And that is why the 5D element, though they are present in the next shell of 4D element, their size is not that much. So basically the lanthanide contraction and actinide contraction, I would rather say lanthanide. Lanthanide contraction is responsible for 4D and 5D element to have a same size. In fact, sometimes the size is that equal to each other that they form chemical twins only. Let me tell you an example. See, zirconium, hafnium, niobium, tantalum, molybdenum, tungsten, all of this. Arey yaar, what is happening? Sorry. Just a sec. Okay. Yeah. See, zirconium, hafnium, niobium, tantalum, molybdenum, tungsten. You know what? What do we call these elements as? Chemical twins. We call them chemical twins. Why do we call them as chemical twins? Because they are having almost same size. Size of only 1 picometer is there difference, or sometimes not even that much. So what does that do? When the, see, in chemistry, most of the properties are decided by size only. So when the size is same, ionization enthalpy becomes same, electron gain enthalpy becomes same, chemical property becomes same. So all those become same. And that is why these three pairs are called as chemical twins. And the sole reason for that is lanthanide contraction. Okay, chalo, moving ahead. Now ionization enthalpy. So as I told you, ionization enthalpy again it has a reason what? Ionization enthalpy is decided by nuclear charge and your size, right? So as you go from scandium to your zinc, ionization enthalpy is increasing. Why? Because the size is decreasing now. So as the size is decreasing, obviously it will be more and more energy required to pull the electron from the outer shell of a given atom or an element. So when you go from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, iron seems to have the highest ionization energy. Similarly, in a 3D element, palladium seems to have the highest ionization enthalpy. And lastly here, iridium, Au, they seems to have the highest ionization enthalpy. Okay, ionization enthalpy obviously has the relationship with the size. Ionization enthalpy and size, they are inversely related. Larger the size, lesser is the ionization enthalpy. Smaller the size, larger is the ionization enthalpy, and so on. Okay, chalo, moving ahead. Oxidation states. Yes, oxidation state. We know that 3D element, 4D element, 5D element, and a block element also. We're gonna move to the block element, but firstly let me finish the D block element. Okay, so as far as D block elements are concerned, see, we know that element react with halides, they react with oxygen, they react with sulfides, they react with hydrogen to form hydrides, carbides, nitrides, phosphides, borides, silicides. Okay, they form different kind of compounds, and in forming those kind of compound, obviously they lose some electron. Sometimes they form a covalent bond, sometimes they form a coordinate covalent bond, and like that. Okay, so different elements shows the different oxidation state. Now, and those oxidation states are decided mostly by their stability in that oxidation state. Okay, so let's see how the different oxidation states shown by the D block elements. So let's see here, scandium to zinc. So whenever you come from scandium to zinc, what do you see? See, the oxidation state of scandium is only and only 3. There is no other oxidation state shown by scandium. Okay, just a sec, let me have this wiring here. Yes, now we can see. Okay, let me have this color. Yeah, look at this. Oxidation state of scandium is 3 only, right? When you go from scandium to titanium, you can see there are 3 valencies, 2, 3, 4. When you go to vanadium, the oxidation states that it shows are 2, 3, 4, 5. When you go to chromium, you see the oxidation state 2, 3, not 4, 5, 6. When you go to manganese, you see the oxidation state 2, 3, 4, 5, 6, 7. So what do you observe from it? In a 3D series, I'm not talking about the other elements right now. In a 3D series, the number of oxidation state shown by given metals keep on increasing. They increases till mid of the series. For example, 2, 3, 4, 5, 6. Right? 2, 3, 4. You can clearly see here 2, 3, 4, 5, 6. And from mid of the series again, it starts declining. See, by showing the highest number of oxidation state in manganese, in iron it shows again 6. In iron it shows 5 only. Not only 5, 3 only in fact, because iron is present only in a +1, +2, +5. Okay. Then in cobalt again it decreases, nickel it decreases, copper, zinc last only. So like that. So number of oxidation state, they started from 1 in scandium and they finished on 1 only in zinc. Okay. So from this 1 to this 1, they went to the highest in the middle of the series. So it kept on increasing like this, again it kept on declining like that. So that is how the trend of oxidation states in a 3D series is all about. Okay. Now look at here. Here the picture is just like that. It is not much change here. Look at here. It starts from yttrium, zirconium, niobium, molybdenum, technetium. So when you go from yttrium, oxidation states are 1, zirconium 2, niobium 3, not 3, 4, molybdenum 5, technetium 4, and ruthenium how many? Almost 6 are there. Again it declines. Okay. So more or less it shows the same trend in 4D and 5D series also. Okay. But there's one more thing that you need to observe here is that which element shows the highest oxidation state? Which are the element here which shows the highest oxidation state? Look at here. Ruthenium. Ruthenium shows the highest oxidation state of 8. Similarly, your osmium also shows the highest oxidation state of 8. And ruthenium and osmium shows this highest oxidation state only and only with the oxygen. That means it forms tetraoxide, RuO4, and osmium also forms OsO4. Oxidation state shows +8. Similarly, here also it shows +8. Right? They could have been bonding with the halogen also, fluorine, chlorine. Okay, but with the halogen, see, halogen and oxygen, both these elements are responsible to to pull or to push the element in its highest oxidation state. But among them also, fluorine and oxygen, they are at the top. These are the two elements, fluorine and oxygen, which are responsible for which are responsible to push the element in the highest oxidation state. Okay, but if fluorine wants to push ruthenium or osmium in their highest oxidation state, which is +8, it is not possible, because fluorine's lowest oxidation state is -1. Okay, so if it wants to push ruthenium to +8, what does it have to do? There has to be 8 fluorine atom to be attached to ruthenium, and osmium also there has to be 8 fluorine atoms. But to arrange 8 fluorine atoms around ruthenium or osmium, it is not that easy. I mean, sterically, it is not possible. There could be a steric hindrance, and that is why oxygen chose to attach with them. And I mean, what's the beauty of attaching with oxygen is that one oxygen can see, each oxygen's oxidation state is -2. So by coming single oxygen, it can push the metal into +2 oxidation state. So to make the +8 oxidation state, there is a requirement of only 4 oxygen atoms. And when 4 oxygen atoms are there, there cannot be that much steric hindrance, because instead of 8, 4 is less, right? Which is obvious. And secondly, there is an advantage with the oxygen is that oxygen forms double bond. So when you form a double bond, there is an achievement of planarity. When the planarity is there, obviously there cannot be a question of steric hindrance, and that is why oxygen tends to bond with ruthenium, osmium, like that. Okay, so remember, the highest oxidation state shown by only 2. Same structure is shown by osmium tetraoxide also. Okay, so the highest oxidation state shown by ruthenium and osmium in the whole periodic table. Okay, chalo, moving ahead now. Now trends in M plus M2, basically this is what? This is reduction potential. Your not actual reduction potential, sorry, my bad. It's an oxidation potential. See, your metals are going from +2 to M, right? So that means your metals are getting reduced. So when your metals are getting reduced, what they will do? They will oxidize the another compound. That means they can act as a oxidizing agent. But this generally does not happen. Metal generally tends to get oxidized. So whenever metal tends to get oxidized, they will reduce the another compound or species. Here I have shown that metal is getting reduced. That means metals are acting as a reducing agent. Okay, and D block elements are weak reducing agent. They are not that strong reducing agent. Okay, so you can see here the copper shown to be here the strongest oxidizing agent. In fact, the reduction potential of copper is higher than, sorry, it is not higher than the hydrogen. In fact, all the metals have the higher reduction potential than hydrogen, obviously higher reduction potential than hydrogen, and the exceptions are copper. After copper you have Ag, Au, copper, silver, gold, platinum, and mercury. Apart from these 5 elements, every metal can replace the hydrogen from its solution, but these 5 metals cannot do that. Okay, remember this thing, it will become handy to you in exam. Okay, now the next thing, trends in M3 plus to 2 plus. So basically your metal is getting reduced here. So when your metal is getting reduced here, what would it do? It will oxidize the another compound. Okay, so M3, so this is metal is getting reduced, but it is oxidizing another compound. So I can call that as the oxidizing power. Okay, so higher the value of this thing, higher will be the oxidizing power. It is that straightforward, right? And if you look at all those things here, look at here, manganese value is plus 1.57, iron is plus 0.77, cobalt is plus 1.97. Do you see this? These values are highest in all. Now here, see, there are some properties which have been studied widely and they have been researched also widely for 3D series only. Okay, you will not see properties of, you will not see every property for 4D or 5D element. Okay, there are some property which have been studied for all the transition element, but some properties are only for 3D metals. Okay, So you can see here, as far as 3D series is concerned, manganese, iron, cobalt, these are having the positive reduction potential for themselves. So for themselves, if they are having positive reduction potential, that means they are ready to get reduced. So when they are ready to get reduced, that means they will oxidize the species which they have come in contact with, right? So therefore, these are the strongest oxidizing element: manganese, iron, cobalt. Cobalt is highest among them. 2 number is manganese and last number is iron. Okay, so that is for the highest number. Now look at the smallest number. Smallest number is for titanium. So titanium is the weakest oxidizing agent here. That is how you can use the standard electrode potential to find out whether given substance is strong oxidizing or weak oxidizing or like that. Okay, chalo, moving ahead. Trends in the stability of higher oxidation state. So as I told you earlier also, that element tends to form higher oxidation state only with the oxygen. Okay, as far as halogens are concerned, you can see here chromium is forming 6 bond with fluorine. Chromium is able to form 2, 3, 4, 5, 6 bond with the halogen. Halogen is what? Halogen is fluorine here, right? So you can see here, fluorine can push maximum oxidation state of +6 for chromium, +5 for vanadium, +4 for manganese, +2, +3 for the iron, cobalt also +2, +3, nickel is +2, copper is only +1 and +2, zinc is also +2, right? So that is what the trends in stability of higher oxidation state. Then oxide chloride. I told you, let me repeat it once again. See, as far as 3D series is concerned, you can push the 3D series in highest oxidation state even if there is no oxygen. For example, here CrF6, your chromium's highest oxidation state is +6 only, and chromium can show 2 compound CrO3 wherein it is in a +6, and it can also form CrF6, there also it is in a +6. So that is possible for chromium, but for the higher element it is not possible, right? This is for fluoride. This is oxide and chloride. You can see here chlorine also is bonding with a different 3D element. Let me have a sip of water now. See here, vanadium is showing oxidation state of +5. Okay, but with the chlorine it is forming only VCl4. It is not forming VCl5. Why? Because of steric hindrance. Because see, chlorine is smaller in size, but chlorine is larger in size than fluorine. So you cannot accommodate all the 5 chlorine atoms to the around the vanadium because there would be a steric hindrance there. That is why it can bond with oxygen to form +5 oxidation state. With chlorine, it can show maximum +4 oxidation state only. Okay, like that. That is how the whole chart is all about. Okay, sure. Moving ahead. Now, sorry. Again, the chemical reactivity, same chart is coming again and again. This chart, I told you about this chart, right? +3, +2, the oxidation state. Now they are going from +3 to +2, so they are getting reduced. That means they are acting as an oxidizing agent. So manganese, iron, cobalt, they are the strongest oxidizing agent in a 3D series. We have discussed about that earlier also. Okay, sure. Moving ahead, magnetic properties. Now, what are magnetic properties? See, there are some species which whenever come in contact with magnet, they show either attraction towards magnet and sometimes they show a little bit repulsion towards the magnet. So basically all the substances which get repelled by the magnetic field, repelled by magnetic field weakly. Any compound which get repelled by magnetic field weakly is diamagnetic, and paramagnetic is what? They get attracted by magnetic field weakly. So any compound which gets attracted towards magnetic field weakly is paramagnetic. Any compound which gets attracted towards any compound which gets repelled by the magnetic field weakly is a diamagnetic. Okay, why does this happen? It all happens because of unpaired electron. See, whenever the electrons are paired like this, what happened? The spin of this electron and the spin of this electron, it is in opposite direction. So they cancels out each other's spin. But if the electrons are not paired, if electrons are unpaired, then their spin is not getting cancelled. So whenever the spin is not getting cancelled, they contribute in the spin magnetic momentum, and that spin magnetic momentum generates the magnetic field, and that is where the magnetic field comes into play. Okay, so how do we find out the magnetic moment? See, this mu effective is equal to n plus 2 pm. What is n? N is number of unpaired electrons. Okay, if you write out all the elements, for example, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, you can clearly see chromium, manganese, these are the elements which are having the highest magnetic field. Okay, because it is very simple. When you put a value of 1 here, what do you get? Whenever the n is 1, you get 1 plus 2 under root 2 plus 1 3 into 1 under root 3. Under root 3 is what? 1.73 something. If your n is 2, what do you get? 2 into 2 plus 2 under root. 2 plus 2 is 4. 4 into 2, 8. Under root 8. Under root 8 is 2.73, something like that. Okay. So let's see the next chart. Look at here. Here the picture is quite clear. Calcium 2 plus and scandium 3 plus. They basically do not have any unpaired electrons. So 0, 0. See, basically D0 and D10. These systems are dimagnetic because you do not have any electron there, right? So if you do not have any d electron, it is obvious for those systems to become dimagnetic. Okay, D1 1.73 pm, D2 2.83, like that, D3 D4. So you can see here D5, Mn2 plus, Fe3 plus, these are the D5 system, 5.92. So basically this number, let me pick it out. See, this number is sufficient enough to tell you how many unpaired electrons are present in your given compound. Because many times what happens is that in a particular subjective exam or even in an objective exam, they have given you the magnetic moment. This is the magnetic moment, spin only magnetic moment. So they have given you spin magnetic moment, and from which you have to find out the number of unpaired electrons present in a given compound, given species, or a given metal ion. Okay, so see here 1.73 D1. You can clearly see here it is correlated like this. This is self-explanatory. And D10 and D0 I have already told you here. Okay, the question was about only D1 to D9. Okay, I hope this must have been pretty much clear for you. Okay, chalo, moving ahead. Formation of color ions. Now, Why do transition metal forms the color ions? Transition metal form the color ion is because of electron present in a d orbital. There should be a presence of at least one d electron. That means d0 and d10 system, they do not show any color whatsoever. Let me write it down here only. D0 and D10 shows no color. That is why I'm writing it in a black color. Well, black is a color, I know. No color. Basically, it's a no color. Okay. So, if your system to have a color, it should have at least one unpaired electron. Your system to have color, it should have at least one unpaired electron, be it D1, D2, D3, D4 till D9. Okay. Now, what happens in color? Let me tell you simple picture here. See, let me draw a color wheel for you. Violet, maybe indigo, yellow. It's like this: VIBGYOR. Oh, sorry, my mistake. Let me erase this. Yes, violet. Then you have what? Blue. Then you have a green, BIBG, yellow, orange color as such is not there, but I will take this. Okay, I'll write red here. This is red, and orange color actually is not there. Okay, this is kind of orange, so I'll take this. Okay, so VIBGYOR. Now, what is value of this? This is what? This is color wheel actually. Okay, this is your color wheel. Now, why I'm telling you about this color wheel? See, whenever your compound, whatever compound you have, which is made up of D block element, okay, D element. What happens is that suppose your compound absorbs the frequency or wavelength corresponding to violet color, then it would look like yellow color. If your compound absorbs the color, so if your compound absorbs the frequency or wavelength corresponding to blue color, it will look like orange. If it absorbs red color, it will look like green. If it absorbs yellow color, it will look like violet, and so on. That is how the color wheel actually operates. So as far as your copper is concerned, copper looks like blue color. Why? Because it absorbs the orange or red wala shade. See, we know that white light is composed of all the 7 fragments. So whatever part of that light which has been absorbed, the complementary of that color actually looks like. Suppose if it absorbs blue color, it would look like an orange. If it absorbs yellow color from the white light, it would look like a violet, and so on. Okay, that is how all these things happen. And secondly, how does it actually happen? Why the given compound have the color? See, whenever your complex compound, where your D block 11 compound, whenever they come into contact with magnetic field, what happens is that d orbital which is having dxy, dyz, dxz, dx square dash y square and dz square orbital. It splits d orbital into two sets. It splits d orbital in two sets, T2g and EG. EG stays above, T2g stays down. Now we're going to talk about that in coordination chemistry. That is why I'm not bringing that here, and I'm not telling you so much details about it. For now, I can only tell you that d block elements or d orbital gets splitted into two parts, T2g and EG. And whenever the electrons in T2g orbital, if it absorbs energy which is corresponding to visible region, it goes to the EG orbital. And whenever it comes from EG orbital to T2g orbital, it releases that absorbed energy. And if that absorbed energy, if it falls in a visible region, your compound appears to show the visible color. Okay, that's the reason D block element complexes or compounds to show color. Okay, chalo, moving ahead now. Now, complex compound. See, D block elements are known to show the complex compound. There are many complex compounds that we are going to talk about in future. There are many complex compounds. For example, like this, K3 FeCN6, K3 FeCN6, K4 FeCN6, or you can say K3C. Oh, sorry, my bad. Like this, or there could be many compounds. Okay, there could be many compounds like this. Now, transition metals, why do they form a large number of complex compounds? The reason for them is a comparatively smaller size. Okay, they are comparatively smaller in size, and secondly, they can hold a very high ionic charges because the incoming ligand, they are coming with a negative charge. Okay, and thirdly, the availability of d orbital, those d orbitals can accept the electrons from incoming ligands. Those d orbital can accept the electrons from incoming ligands, and that is how they form the different kind of complexes. Okay, we're gonna understand about them with a much more detail in a chapter called coordination compounds. Okay, let me rub it down again. So these compounds are visible for you then. Yes. Array, what is happening? Yes, look at this. They can show compounds which is having a different geometry ranging from linear, trigonal planar, square planar, tetrahedral, trigonal bipyramidal, square pyramidal, octahedral, trigonal prismatic, and so on. There are different kind of geometries, okay? But anyways, which we're gonna see with a much more detail in a chapter called coordination compounds anyway, okay? So let's move ahead with this now. Now, catalytic property. See, transition elements are known to show, they are known to behave as a catalyst in a different range of reactions. Okay, transition elements, as far as catalytic industry is concerned, transition elements are very useful. Okay, why they are very much useful is that because they can show, they can show these catalytic properties because of variable oxidation state. They can shuffle between these oxidation state very easily. They can adopt different oxidation states. They have a very large surface area. They have a free valencies available. All these properties contribute them to have a very good, all of these properties come together for them to show a very good catalytic property. Okay. For example, vanadium oxide in contact process. In contact process, what actually forms is that we take the sulfur, we combine it with the oxygen to form SO2. Okay. Then SO2 gets converted to SO3, which is the most important process in a contact process. What does contact process do? Contact process prepares the sulfuric acid, and it prepares the sulfuric acid from sulfur. It converts sulfur into SO2, and then SO2 gets converted to SO3 via vanadium pentaoxide, and that SO3 is then fused with the previously formed sulfuric acid in earlier batches. Then it forms oleum. Oleum then reacts with water to form sulfuric acid. Okay, let me tell you how. See, in contact process, SO2, I will write 2SO2, O2. They react like this in presence of V2O5, vanadium pentaoxide. It forms 2SO3. This SO3 then combines with sulfuric acid to form H2H2O7, oleum, which then reacts with water to give you 2 moles of sulfuric acid, which we will see in P block element surely. Okay, here I just have to tell you where do we use this particular catalyst. Okay, similarly, finely divided iron is used in a process called Hebbe's process, formation of ammonia, as we all know, the very important process. N2 3H2, it gives you 2NH3, like that. Okay, that is how you can see the formation of ammonia. Obviously, finely divided iron is there. Along with iron, you also use molybdenum, okay, as a co-catalyst. And lastly, nickel in a catalytic hydrogenation. You have ethylene, CH2, CH2 reacts with hydrogen in presence of a catalyst called Rani nickel. That gives you saturated hydrocarbon. This process, nickel in a catalytic hydrogenation, this process is actually used to convert vegetable oils into vanaspati ghee. You might have heard about dalda ghee. So formation of dalda ghee comes into this reaction, catalytic hydrogenation. Okay, sure. Moving ahead. Yeah, the reaction. This is how different compound get actually adsorbed. You must have, if you have understood this reaction, let me rub it down. What is happening? Yes. See, these are the metallic atoms. These are the gaps. These are the surface area available, and this is how different reactant gets adsorbed over them. Okay, it is all actually adsorption, and we're gonna cover this in a chapter called adsorption also, surface chemistry. Then we're gonna see what this adsorption is all about. Okay, फिलहाल के लिए आगे निकलते हैं. So, formation of interstitial compounds. See, D block elements are known to show a different kind of interstitial compounds. जैसे कि हाइड्रोजन, कार्बन, नाइट्रोजन, कभी कभी तो बोरान भी होता है. So, जो D block element है, this D block element have the crevices in them. In those crevices, this non-metallic element, for example, हाइड्रोजन, कार्बन, नाइट्रोजन, बोरान, सिलिकॉन, जो साइज में छोटे हैं, वो इन क्रिवाइसेस में जाके बैठ जाते हैं. और जब कभी वो क्रिवाइसेस में जाके, जैसे देखो यहाँ पे कार्बन जाके बैठ गया, ये पूरा आयन का स्ट्रक्चर है. इन द स्ट्रक्चर ऑफ आयन देयर इज सम स्पेस हियर. in that crevices or interstitial carbon has got. और जब कभी भी ये नॉन एलिमेंट जब कभी भी ये नॉन मेटल इन मेटल के क्रिवाइसिस में जाके बैठ जाते हैं, it actually changes or modifies the property of a given metal. Okay. Alloy formation. See, different metal form a different alloys. Now we know that D block element, they are mostly of same size. So since they are mostly of same size, it is quite easy for them to fuse together and to form a solid, solution. It is quite easy for them to form the solid solution. That is why they easily get fused and they form the alloys. Okay. Now that we have done about D block element, let's study some of the F block elements. ठीक है, D block element खत्म हो गए, अब जाते हैं F block element की तरफ. इनर ट्रांजिशन एलिमेंट जिनको हम लोग बोलते हैं, राइट? ओ सॉरी, माय बैड. डी ब्लॉक एलिमेंट हो गया. अब डी ब्लॉक एलिमेंट के कुछ इंपॉर्टेंट कंपाउंड जैसे कि K2Cr2O7 एंड KMnO4. So K2Cr2O7 and KMnO4, these are the two strongest oxidizing agents. These are the very two strong oxidizing agents. Okay, and how they're gonna behave in a different kind of reactions that we gonna see. Okay, potassium dichromate K2Cr2O7. It is generally orange in color. You can see here, it is orange in color, chromate ion, and the structure, if you're going to talk about, this is the structure is Cr2O7 2 minus. That 2 minus is counterbalanced by your 2K plus. Okay, स्ट्रक्चर तो वैसे तुमको पता ही होगा, इतना कोई डिफिकल्ट स्ट्रक्चर नहीं है. इसकी प्रॉपर्टीज ज्यादा इंपॉर्टेंट है. Look at the property. See, K2Cr2O7 is a very strong oxidizing agent. Very strong oxidizing agent. How? See, K2Cr2O7 on reaction with sulfuric acid, it gives you chromium sulfate, H2O, K2SO4. It releases 3 oxygen, and you can see here the oxidation state. The oxidation state of chromium goes. The oxidation state of chromium goes from +6 to +3, and each chromium has gone from +6 to +3. That means each chromium has got reduced by a factor of 3, and there are two chromium atoms, right? So factor of 3 into 2, kitna ho gaya? 6. So overall, this compound changes its oxidation number by a factor of 6. Basically, it gets reduced by a factor of 6, and that is why it can act as oxidizing agent by a factor of 6 only, and that is why the end factor for your chromium is 6. So whatever compound it comes in contact with, it oxidizes those given compound by a factor of 6 in acidic solution. Potassium dichromate, this K2Cr2O7, cannot act as an oxidizing agent in basic medium also and in neutral medium also. It can only act as an oxidizing agent in acidic medium. Okay, let's see how. See, iodide to iodine. So iodide to iodine, whenever you are to write the reactions about this, no, you should always understand that whatever species you are oxidizing, by what factor it is getting oxidized. For example, your iodine is in a -1, and here it's in a 0 oxidation state, right? So there is a change of oxidation number by +1, right? So how many iodine you can take? You can take 6 iodine, right? For example, the chromium Cr2O7 2 minus, right? From there, your chromium is going in +3 oxidation state. Now I am writing only ionic reaction. Okay, I am writing only ionic reaction. Here it is in a +6. Here it's in a +3. Cr2O7 2 minus. So now your iodine 6I minus. From that it can form 3I2. Okay, oxygen, 7 oxygen are there. So you basically form 7H2O and 14 hydrogen are there, 7 into 2, 14. So you get 14H plus, and that is how your reaction has got balance. Okay, you must have seen balancing reaction in this way in 11th standard in a chapter called redox reaction. Okay, here I am only going to tell you, or here I am only telling you how you can balance the change in oxidation number by using the different oxidizing agents. Okay, so similarly you can convert H2S to S. Now whenever you are converting H2S to S, sulfur here is in a -2 oxidation state and here it's in a 0, right? So you are going from -2 to 0. So increase in oxidation number or decrease, yeah, increase only is +2, right? So we can take only 3 sulfur. So whenever you can take 3 sulfur only, how would you write it? Cr2O7 2 minus plus 3H2S like that, 2Cr 3 plus 6 plus 3 3S 7H2 14 8H plus. So that is how you can solve a different oxidizing reactions. Okay, chalo, moving ahead now. Potassium permanganate, KMnO4. It's a purple color compound. Potassium permanganate is a purple color compound. Okay, you must have seen in the laboratories. The structure is KMnO4 magnet, tetrahedral in color, and obviously what happens here? There is a resonance. So double bond would come there like that. Okay, tetrahedral permanganate, purple green color. Okay, structure I'm not going to discuss much about. I'm going to discuss about their oxidizing reactions in acidic solution. Now see, K2Cl2O7 or potassium dichromate was oxidizing agent only in acidic medium. Whenever you change it to the basic medium or to the neutral medium, it cannot act as the oxidizing agent. Okay, but that is not the case. That is not the case for KMnO4. How? See here, KMnO4, as far as KMnO4 is concerned, here your manganese is in a +7 oxidation state. From there it goes to +2 oxidation state. So change in oxidation state is what? 5. N factor is 5. So whatever compound you are oxidizing in with the help of KMnO4, make sure its oxidation number increases by a factor of 5. Okay. Similarly in alkaline solution, see, in alkaline solution you can see here oxidation state of manganese is +7, right? And here it's in a +6. So it's changing by a factor of only 1. And lastly, in neutral solution, again manganese is obviously it is in a +7. From there it goes to +4. So change in oxidation number is 3 only. So you can perform or you can try to write the reaction the way we have written for K2Cl2O7 for I-2 iodine and H2S for by taking KMnO4 also. Obviously in a different medium, acidic medium, basic medium, neutral medium, because there had been a question asked on this kind of, there have been question asked on this topic many times. They'll give you given compound which is to get oxidized, then KMnO4, they might not give you medium, they will just write H plus. Now you need to understand if the H plus is there, that means medium is acidic. Sometimes they might write OH minus, so then it's a basic medium. Sometimes they will just write the water, that means medium is neutral. Okay, sometimes they will not mention all these things. You need to understand from all the reactants species. Okay, sure. Moving ahead. Now that we have understood all the D block elements, their different kind of compounds, let's understand the F block element. Okay, F block element. Lanthanide, actinides, as we all know. Lanthanides. What are some of the lanthanides? Lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, then thulium and terbium. And actinides series is actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, californium, berkelium, einsteinium, fermium, mendelium and nobelium. Okay, now let's understand how to see. I know that it's very difficult to remember all the F block element. Okay, and that is why I have brought mnemonic for you. I have brought a mnemonic for you to understand all the F block element very, very easily. Okay, now let's try to remember all the F block elements through mnemonics. Okay, let's see. How can I remember? Now pay attention very carefully. Last century presented new democratic prime ministers. Last century presented new democratic prime ministers on social media. After that, European government decided to ban dirty hotels to make yellow buildings luxurious. Okay, now how can we correlate this with the different kind of metal? For example, first is lanthanum, last century CE, cerium, then PR, praseodymium, right? Then new democratic ND, neodymium. After that, prime minister PM. So what do we have here? PM, promethium. Lanthanum, cerium, praseodymium, neodymium, promethium. On social media, SM, samarium, SM, samarium. European government, EU, European government, GD, decided, no, GD, gadolinium. Government decided, GD, gadolinium. TB, to ban, TB, terbium, TB, terbium. Dirty, DY, dysprosium, DY, dysprosium. Hotels, HO, holmium, hotels, holmium. And lastly, you have what? TM, not lastly actually, TM, thulium, to make, thulium, TM. Then yellow building, YB, terbium. I know it sounds like funny. Terbium, but it is like that. YTTERBIUM, like terbium. And lastly, you have LW, lawrencium. So That is how, by using this mnemonic, you can remember all the Ed block element very easily. How? Last century presented new democratic prime ministers on social media. European government decided to ban dirty hotels to make yellow buildings luxurious. So last lanthanum, C century cerium, present and PR praseodymium. Then you have a new democratic ND neodymium. Prime Minister PM promethium. Then you have on social media SM samarium, European. Then you have government decided GD gadolinium. Then two band TB terbium, dirty DY dysprosium, hotels holmium, to make thulium, yellow buildings terbium, and luxurious LW Laurentium. That is how you can remember all the lanthanide series very easily. Okay, chalo, moving ahead. Now electronic configuration. See, as far as electronic configuration is concerned for lanthanide, again lanthanide series actually starts from where? It starts from actually 58. Cerium actually is the first lanthanide element. Remember, La, which is lanthanum, is not lanthanide element. It's a D block element. A block element, the first series of A block element, which is lanthanide, it starts from them. That is why it has been named after lanthanum. Okay, but it starts from cerium only, because you can clearly see here the F electron enters into cerium. It is not present in a lanthanum. That is why lanthanum is a D block element. So you can see here cerium 4F1, 5D1, 6S2. Till here it seems like pretty good, okay, but immediately look at this 59 electronic configuration. 4F1 is cerium, so praseodymium should have been 4F2, but no, it is 4F3. Okay, that is where the exceptional electronic configuration is coming. 4F3, 4F4, 4F5, 4F6, 4F7. Now here from 4F7 it is becoming 4F7, which is absolutely right. Why? Half filled. Remember, as it has happened for chromium, where the half filled d orbital was happening, similarly half filled f orbital would also try to complete its half filled electronic configuration. That is why from 4F6 it immediately becomes 4S7. It stays 4S7 in gadolinium. Okay, why? Half filled f orbital. But the exception is coming in 65 terbium, because there from 4F7 it becomes 4F9. Okay, that is the exceptional thing. So here 59 and 65, these are the two atomic numbers that you need to remember for the exceptional electronic configuration. Here you are having extra F electrons. Okay, so these are the some numbers that you need to remember. For example, for D block element, first it was chromium and then copper, right? So it was what? 49, then you have a 368 in 4D series, and 5D series you have a 8. Similarly, you have a 59 and 65 where the exceptional electronic configuration is present. Okay, sure. Next, atomic and ionic sizes. Now, as far as atomic and ionic sizes is concerned, you can clearly see here, this is the classic example of lanthanide contraction. Size decreases as we all know that in lanthanide also you are moving from left to right. The size is going to get decreased, which is obvious. But size is not getting decreased that much. Size is getting decreased from 104 to 86. In this 18 picometer, mark my word, okay, mark this very clearly. In this 18 picometer only, there are 14 elements. 104 to 86. This is only 18 picometer. 18. इस 18 पिकोमीटर में 14 के 14 ए ब्लॉक एलिमेंट ठूस दिए गए हैं. उस वजह से क्या होता है, बहुत सारे ए ब्लॉक एलिमेंट की साइज ऑलमोस्ट सेम होती है. Okay, that is why this kind of contraction has been named very differently as lanthanide contraction. Okay. So moving ahead, oxidation state. See, the main oxidation state that you can see here is that +3. They would always seem to show +3 oxidation state. So you can imagine lanthanum to behave just like aluminium. You can imagine lanthanum to behave just like aluminium. They show the similar oxidation state as aluminium. I mean, they can show +2 and +4 oxidation state also, but their main oxidation state is +3 only. Okay, chalo, moving ahead. General characteristics. Now these are the general characteristics. As I told you, lanthanum, you can imagine lanthanum as aluminium. So you can imagine lanthanum as aluminium because they are behaving just like that. Look at here. With halogen, it is showing LnX3. It reacts with water to form LnOH3, where it again is +3 oxidation state. It releases the hydrogen. It reacts with nitrogen. See, nitrogen is in a -3, so lanthanum is in a +3. With nitrogen, it's forming nitride, lanthanum nitride. Here it is forming sulfide. Again, 3 sulfide and -6. 2 lanthanide are in a +6. Divided by Q, it becomes +3. Similarly, here also +3. So you can see all this reaction. It is predominantly shows +3 oxidation state only. Okay, now let's look at the actinides. Actinide, actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelium, and nobelium. That is how all this actinide series is all about. Okay. Now let's understand. Now let's try to remember all the actinide series through mnemonics. How? Let's see. So firstly, we can directly write the actinides, 3 planets, Uranus, Neptune, Pluto. Uranus, Neptune, and Pluto. Okay, after that we have, now let's remember all the actinides through mnemonics. Now let's see how these mnemonics are. Actinium, 3 planets, Uranus, Neptune, and Pluto. Then you have America, cured, Berkeley, in California. Then Einstein, Fermi, Mendeleev were Nobel laureates. Now that I have told you all the mnemonic, let's see how to extract the element from it. Okay, so actinium as the first element we must have understood, actinide, actinium. Then 3 thorium planets, protactinium. This is uranium, obviously, neptunium and plutonium. And these three are very easy to predict, right? Actinium, thorium, protactinium, uranium, neptunium, Pluto. Then Am, americium. Then curium, berkelium. Obviously these all were the name of scientists, right? Americium, curium, berkelium. Then you have a californium, einsteinium, yes, Fm, fermium, Md, mendelevium were Nobel laureates, NO, nobelium. Last one obviously is lawrencium, but that is not, sorry, yeah, lutetium. Last one is lutetium. So that is how all of this are the lanthanide and actinide series. So these are the trick, or these are the mnemonic that you can use to remember them. Now electronic configuration. Electronic configuration, mostly they will not ask you about the F block element that much. It is not that much important for your CBSE exam, because they will ask you mostly about which element present where and all that. Okay, but still, if you want to see, you can see the electronic configuration 61, 60, see 50, 50, 52. See, instead of coming 50, directly 52 has come. So F1 is not there. 2, 3, 4, 5, 5 also not there. F1, F5 is not there. 7, 7, 8 and 9. This is how I can help you to understand and to remember. F9, F1 and F5 are not present. You can see here. F0, 0, directly F2, then F3, F4, F6, F5 is not there, F6, F7, F7, F8, F9 is not there, F10, 11, 12, 13, 14, like that. So F1, F5 and F9 are not there. Other F orbital electrons are there. You can find that out. Okay, chalo. The next one, ionic sizes. Ionic sizes of lanthanides and actinide, it is not that much different. The same way the lanthanide has shown contraction, actinide also shows contraction, which is called as actinide contraction. Okay. Oxidation state. See, oxidation state, just like lanthanum, actinide also shows the typical oxidation state of +3. You can see here the typical oxidation state is +3. Thorium is the only element which shows only one oxidation state, that is 4. Okay, and yeah, otherwise it is mostly the same thing only. So there, general oxidation state of lanthanides and actinide is +3, but there are some elements, for example, in the lanthanide cerium and here thorium. These are the two elements which shows +4 oxidation state also. Okay, so moving ahead, general characteristics. See, all the actinide elements are radioactive. All of them are radioactive. These elements, they do not have any stable isotope as such. Obviously they tarnish in air. Okay, they are very dense metals, distinctive structures, they are fairly soft, malleable, ductile, and yes, they are very highly paramagnetic because they are having high number of unpaired electrons. Okay, generally they combine directly with the most non-metals. They are very reactive metals. Okay. Now comparison. If you want to compare lanthanides, actinides, most of the properties are similar only. Okay, but the thing is that most of them are similar. Where do we have a difference is that in lanthanide, except promethium, all are non-radioactive. In lanthanide, only promethium is radioactive. In actinides, all of them are radioactive. All of them. Okay. Secondly, these compounds are less basic lanthanide. Actinides are very, very basic. So these are some of the differences. Then lanthanide do not form oxocations. Actinides form oxocations. So these three are distinctive differences. Other than that, mostly they are same metal. I mean, mostly they show same properties only. Okay. Now, some of the applications of a block element. A block element has been used in a mixed metal refractories. Okay, mostly in this nuclear reactors, cleaning glass, cancer treatment, atomic fuel, nuclear bombs. There are multiple applications that you will see a block element are being used, and in some components of integrated circuits or some components of your smartphones in today's day, also a block element is being used. Okay, and lastly, this is the nuclear reactor. In nuclear reactor, we all know uranium is a very famous radioactive element. Okay, so most of the a block element, they, for example, plutonium, uranium, neptunium, they are being used as a radioactive metal to obtain the energy from it. Okay, I hope all of this is very much useful for you. Okay, we are going to come with different kind of chapters just like that. Okay, thank you everyone. Bye bye.
Bring learning alive practically.